Yeah, so I'm Thomas Oettinger. I'm a Senior Research Director at Oracle Labs. Oracle Labs is the successor organization of Sun Labs, and Sun Labs is proud to be at least partly the source of Java. And at Oracle Labs, we do still quite a lot of VM and programming language research. At this stage, actually, the largest part of Oracle Labs is in that domain. And we are focused on a project that is called Graal. And I will quickly introduce Graal's project vision architecture and how that is connected with the Java virtual machine. So Graal's problem statement is basically to realize the world is very polyglot. And if you look at the TOB programming language index, you see Java is still leading in terms of the main language. But there's more and more languages that become relevant. And even on Java, there's a lot of languages that leverage the platform and that are new and hot, like Kotlin or Scala. And we actually think that there's a lot of value to the platform. It should be leveraged by a lot of languages, but we actually want to extend this not just to languages like Kotlin and Scala, but also to languages like JavaScript, Ruby, or also the R programming language. So the project vision for Graal is to create a high-performance polyglot language-level virtualization layer, and one that is embeddable and not only in JVM-based applications, but also native applications. I'll later show why we think we can achieve that. Graal's base architecture is that it's based on the Java hotspot VM, which is a production quality Java VM, and in the recent version, there was a JEP 2.4.3 introduced in JDK 9 that allows to, for the first time, to program a JIT compiler in Java, written in Java, and plug it into the VM. So it makes the VM pluggable with this JIT compiler. On top of this JEP, on top of this JVM CI, we built the Graal compiler, and that can run all of the normal Java languages. But we have extended that to include a framework that we call the Truffle framework that brings languages into the JVM universe that previously have been out of that universe. And this includes Ruby, R, and JavaScript as one of the examples. And the Truffle framework is really the framework that removes the problem of matching, for example, JavaScript to Java bytecode. And it can execute then the JavaScript at high performance on top of the JVM. And it's not just JavaScript, it includes Node.js support, full Node.js support on the JVM. And in addition to the Node.js support, it also includes Solong, which is our project code name for bringing LLVM-based languages also into the managed environment. This allows them to execute C, C++ code on top of the JVM. And this execution is just not possible at high performance by individual languages, but it also includes interoperability. So it allows you to mix and match those languages. Anyway, I guess you just have to look at Ming's slides. So it allows to mix and match the languages, and to kind of talk from JavaScript to Java and the other way around without any issues. And there is one more thing, like one more slide I had here, which was on that Graal itself is not only able to execute on top of the JVM, on top of the hotspot JVM, but it can also execute standalone. So you can use Graal to create a standalone executable that with fast startup and low footprint. And this standalone executable can be embedded in native applications, C applications. And well, one of the reasons we are doing the project is we want to embed this execution environment in data processing applications. As Oracle has some data processing applications that are quite important to the company, we actually want to bring the ability to run these languages not only to the Java virtual machine, but also to data processing environments like MySQL, Oracle DB, or similar things. So I think there's a lot of value in the Java platform, and our vision for the Java platform is to become more polyglot and to become more embeddable. Thanks.
It wasn't on my computer.
Just
Oh, it's fine.
Break the barriers. Good. Okay. So we think JVMs are cool views over snowflakes. That, by the way, is Crater Lake. So I'm Gil Penn, I'm the CTO at Azul Systems.
Could you use the mic, please?
Testing? Yeah. Okay, I'm Gil Tene, I'm the CTO at Azul Systems, and at Azul we build JVMs. That's all that we do. I think we're probably the only company that is purely working on Java, JDKs, JVMs, and nothing else. That's, well, because we're much smaller than these two companies. And we actually have two different products that we have, that we ship. One of them is called Zulu, one is called Zing. They have different qualities. So Zulu is actually OpenJDK. So I might be here talking about how great OpenJDK is, because it is a really cool project. It's mostly built and driven by Oracle, but there is a very good community participation. And OpenJDK as a project produces source code. It doesn't produce any binaries. That source code then ends up in other people's JVMs, ours included, and in the Oracle JVM, and parts of it end up in various forms in IBM's JVM. For example, the class libraries in Java are probably not done anywhere else in clean source. It's taken in some way, one way or another, through that project. Zulu is a pure build of OpenJDK. It's 100% open source. It stays true to the project itself. We will fix bugs here and there and upstream them. And the main place that we might make things different or differentiate is when we build embedded platforms and have to do JIT compilers for ARM32, PowerPC 32, variants of ARM64. But primarily that's OpenJDK, the vanilla JDK you're probably used to. Zing is where Azul puts the differentiation. There are various areas of differentiation, but probably the biggest one is speed. And I'll quickly go through what we think of as speed and what Zing provides there. But the thing to highlight, I think, is probably one of the differences is we're talking about current. This is what we actually ship today, not what we're thinking of doing 2 and 5 years down the road. There's also really cool stuff there that I'd love to talk about. But when we look at speed, generally speed is what you want to see speed look like this, but it doesn't really look like that. In Java, speed tends to look like this. It starts slow, it gets faster, it bumps around a bunch, goes up and down, maybe stabilizes, and so on. And that has 3 main components. One of them is how JIT compilation works. So you start with interpreted code, or slow compiled code in some other versions that have existed. And then you get better. As code gets hot, you pay attention to it, you optimize it, you put some profiling into it, and eventually you get this nice blue stuff that's clean blue code. On the way there, you try things, you fail, you go back and forth. That's what speculative optimizations do, and then de-optimizations. But eventually you hope most of your code becomes nice and blue. In response time, it tends to look like this. You start slow because you interpret it, you get faster and faster over time. You eventually stabilize at this nice blue thing that may take a while, like many seconds or maybe even an hour if you're not running that fast. And then along the way you have all these blips, GC pauses, other pauses, etc. If we think of this from a speed perspective, this is what speed looks like. It's the inverse of response time. You start slow, you get faster, and you get faster, and you get faster as you learn new code profiles, etc. Eventually you get to full speed. But even at full speed in Java, you generally have these dips to an absolute zero speed for a little while. A little while might be 5 milliseconds, might be 50, might be 500, might be 5 seconds. If you've got a terabyte heap, it might be 3 minutes. But there's a little bit of zero speed, then you go back to being fast again. The simple way to map what Azul does about does in product is we fix the 3 different aspects, or we address the 3 different aspects in speed. Falcon is what we call our JIT compiler. It optimizes for faster code. What faster code does, the speed is easy to understand. It makes it faster, it raises the bar. Ready Now is a set of features we have focused on not going through this climb to speed every time you start a JVM, but starting it at speed, especially trying to make sure that the first actual critical operation you do is already running at speed, or the second critical operation you do is running at speed, rather than go through 10,000 training runs until you actually get to speed. And if you think of what that means today in environments that deploy code 70 times a day, when 70 times a day, every one of your servers has experienced 10,000 slow transactions before they get to speed, that's a big deal. If you want to think in New York terms, maybe think of market open. When at market open, the first 10,000 trades are slow, you lose money. Other people take your lunch. And the last part is C4 takes away, C4 is our garbage collector, it takes away these dips. So basically our aim is to get to this nice flat speed like you, or close to the nice flat speed you'd like to see. To be honest, you're never going to get to the flat speed you want to see. But we get there we get much closer to that, and we keep raising the bar. Last part I'd like to say, within what we have in the JVM, we've recently come out with a new JIT compiler for Zen. We completely replaced the traditional C2 compiler, the tier 2 optimizing compiler and hotspot in Zen, with something we call Falcon. Falcon is pretty easy to understand if you think about it as taking LVM, which is an open source project that has compiler optimizations for many languages, many platforms in it, probably one of the main focuses of compiler optimizations around the world. And we basically allow LVM, or use LVM as a code generator, optimized code generator for the JIT compilation. Falcon is the wrapper around that. And you can think of us as taking a lot from LVM and making it work, but we also put a lot into LVM. Over the last 3 and some years, we ran the Falcon project to make LVM generated code work in an actual product JVM. In order to do that, we had to dramatically change things in LVM itself. We had to enable LVM to do things that conceptually it was thinking of but didn't quite do very well. For example, the optimization and dealing with the fact that GC safe points exist in the world and GC barriers. These are all concepts that were thought of, but if you turn them on, you basically lost all other optimizations, or almost all. We've changed LVM to the point where all these practical optimizations that other JVMs have been doing for a while are possible within LVM, and we get them in all the other optimizations combined. We've upstreamed all of that. So LVM today, at the top, is very different than LVM was 3 years ago. We think other runtimes are going to be able to leverage the same things that we put in there for things like .NET with LVM, or we're talking with the Pony guys, for example, that are LVM based. Other runtimes will also be able to use this if they want to do highly optimized JIT compilers. So with that, I'll hand it over to our friends from IBM. Hopefully this works.
Yes, it works very well.
He ran away.
Optimized away.
Hi, so I'm Dan Heidinga. I work for IBM. I'm the J9 interpreter team lead. I've been with IBM about 10 years now and touched most of the core of the IBM runtime. So here's the one slide. Everybody gets sick of at most conferences. It makes my lawyers happy. So, I'm going to start off by saying that OpenJ9 is the #1 cloud runtime. How many of you are actually deploying to the cloud these days? Seeing hands, yeah. Does everybody know how cloud accounting works? Basically, you're paying for the memory that you're using. In most cases, it's not the compute that you pay for, it's the memory. And what we found is that over the years, there's been a pendulum in Java. It's swung from, peak throughput has been the only thing anybody cares about to today people are caring about startup and footprint a lot more. And what I like is we took a typical Java application, Acme Air, which is one of these cloud apps, and we ran it on OpenJDK, and we ran it on J9. And assuming you had an 8 gig box, you could fit about 5 instances of OpenJDK there, and you could fit 16 of J9. So if you're looking at paying for cloud, if you're looking at running in the cloud, J9 is going to get you more throughput at less cost because we're going to use less memory. So where do you get it? Well, right now you can grab it from Docker. Docker pull IBM JDK, or Docker pull IBM Java, sorry. You can get a JRE there, you can get a JDK, and you can also get something we call SFJ, or small footprint Java. This is a stripped down JDK. It's still compliant, but it has fewer features and gets you a better memory size or a smaller Docker image, which really matters as you start deploying into the cloud. We also support Alpine Linux, not just your standard Linuxes, but Alpine, as the images there tend to be a lot smaller. So I've been saying OpenJ9 is the #1 cloud runtime, and a little bit more background on J9. It was designed by the ground up from IBM. IBM has thousands of products that run Java, and so over the years we've had to develop a VM that runs on everything from cell phones all the way up to mainframes. And we had to focus on high performance, on being able to service this runtime, on being able to ensure that we were getting optimal performance for our workloads. And not only our workloads, but also our customers' workloads. So why do we believe we're the #1 cloud runtime? Because we're DevOps friendly, we have high performance, we exploit the platform deeply, and we're cross-platform. So when I say DevOps friendly, to support the VM, we've had to build a lot of tools in to make sure it's easy to tell what the execution is doing. So we've got a trace engine that traces important events as you're running. We have a dump engine that lets you generate Java cores, heap dumps, system cores, JIT dumps, all kinds of diagnostic data at any point in time so you can understand what the JVM is doing. The days of being able to write an application and toss it over the fence to your operations team and ignore it are rapidly disappearing if they're not gone already. And so being able to get this kind of high quality data out of your JVM to understand what it's doing is increasingly important, especially for developers as you're hacking on things and building your application. So we've got a lot of tools built into the VM to show you what's going on. And then we've got a lot of free diagnostic tools. We've got Health Center, which is like mission control. It gives you diagnostics and monitoring. I mentioned the dump engine earlier. It lets you take a system core. And then if you really want to, you can use a tool like IDDE or JDumpView to dig through the native JVM structures to understand what's going on in the runtime at any given point in time. And then for garbage collection, tuning, and monitoring, we have GCMV. One of the little things I'd like to call out, as it's a fairly new feature we added, is we noticed that people were doing uber-jar deployments. Java-jar, some jar doesn't really leave you a nice place to put your command line options. So we said, okay, let's add them to your, at least the default options, to your manifests, and the VM will read them out of there. We also do a lot of tuning for virtualization and idle detection. And we're high performance. I've mentioned this already, but we start up faster than OpenJDK. especially in tuned workloads, we're half the footprint, the same throughput. And I've mentioned a bunch of things here. Single word object headers, so your objects are smaller, you get more of them on your heap. Got our GC scales. We've done a lot of work to make sure that not only do we give you good single thread or low number of core performance, but as your boxes get bigger, we scale across that. Whether that's large heaps or large compressed refs heaps. And we're exploiting things like GPU, SIMD, dynamic AOT. You don't have to worry about what code to AOT. The VM is going to detect that, store that AOT code away for you, and be able to reuse it and run it again later. We're cross-platform, Windows, Linux, AIX, ZOS, and then name the hardware we basically run on it, which is a really cool thing because it keeps us honest. It means no cheating, no paying attention just to x86. You really have to make sure that the algorithms you're using are well-tuned and that you're catching all the bugs that other platforms are going to shake out for you. And then not only do we run on a lot of platforms, but we can exploit them. We work with hardware vendors to make sure that the features the platform offers are things that we're going to use and going to be able to expose through Java. Whether that's GPU and explicit control using our CUDA for J APIs, or automatic exploitation by the JIT when you're using operations like arrays.sort or Java 8's parallel streams. And then of course there's vector operations as well. This is making sure that you're able to run a single instruction across multiple data to get better performance. Runtime instrumentation. If your hardware provides ways for the VM to track what it's doing, we're going to use it. Hardware compression, better access for native data, RDMA. There's a lot of really cool deep exploitation of the platforms built into J9. And so one of the things you've heard mentioned, everybody talk about a little bit, is Polyglot. And our story is built more around Eclipse OMR. So we looked at our JVM and we said, hey, we have an amazing production-ready, battle-tested JIT compiler. We have an amazing garbage collector, several different policies there, and we have a lot of platform support code to be able to take a runtime and run it on multiple platforms. So let's take that core investment we made in Java and refactor out the parts of it that aren't Java specific, so that you can run your other languages on the same kind of code. You can uplift all the other polyglot languages that you're dealing with to get better performance for them as well. And then you can use one set of tools so your operations work well across whatever language you're working with. So we open sourced this in March of 2016. And I just want to point out the license is EPL v1 and Apache 2.0. So it's very friendly to anybody who wants to pick it up and run with it or pick it up and use it. We'd love to have contributions and to work further with other people. I'm just going to stick this slide up here. It's a quick list of some of the components that we put into the OMR project. The one I always like to call out is JIT Builder. This is a great library for anybody who wants to get started on adding a JIT to some language. It makes it very easy to get up and running without having to understand all the intricacies of dealing with a JIT compiler. So talk about Eclipse OMR, which is a great community for building other languages, for answering the polyglot question. And as Gil said, everybody takes the class libraries from OpenJDK. We do too. We just replace Hotspot with a runtime of our own, with J9. It's built on top of OMR. And the rest of our runtime is going open. You'll be able to find J9 hopefully before Java 9 ships, or before we ship our Java 9. So you'll be able to see the full open source stack top to bottom.
Thank you, Thomas, Gil, and Dan. Certainly, this is a user group meeting, so if you have questions that you want to ask the gentleman up here, feel free. So I can run down there and give you the mic. But I have some questions and some discussion points. So here I'm a Java developer, I have a Java application. give me like a 1 sentence, 2 sentence reason why should I use your JVM?
As I said, we're the #1 cloud JVM. If you want fast startup, you want less memory used, you want to pick J9, you want to run across multiple platforms. We're the one.
I have 2 JVMs to talk about. so for OpenJDK, which Zulu is the most popular binary distribution for OpenJDK, it's because it is the binary of OpenJDK, which is the most popular platform out there, also in the rest. And that's a simple, easy answer. That is OpenJDK. For Zing, it's very simple. It's the best JVM out there to run your code today, metrics-wise. You don't like GC pauses? That's what Zing is for. They're gone. You want fast code? We've got the best JIT out there today, not tomorrow, not in the future, not in some other thing. And you saw what Ready Now is too. So that was a little more than this.
So Zing is not based on OpenJDK?
Zing, it's similar to how the J9 thing is. We share a lot of the class libraries. We share virtually all of it. But Zing is a proprietary JVM running the same stuff. It is based on the same hotspot code, but with dramatically replaced internals. J9, I believe, is more of a clean room implementation of a JVM. You can think of Zing as having its heritage with hotspot, but the GC is different, the JIT is different, the interpreter is different, the C1 is different, the threads are different, the logs are different. Yeah, but the heritage is similar.
Either because you want to combine it with Node.js or other types of languages like R or Ruby, or if you want to AOT compile it to native code and embed it somewhere. I think that would be the main functional differentiators. Performance-wise, we can discuss the topic in more detail, because I do not 100% agree with the statement that performance benchmarking, I think, and that might be the most controversial topic to go into. But let's say there are some workloads, in particular workloads around Scala or Kotlin workloads, where actually we think that we are best. But, yeah.
So and it's not just Graal, we're talking about the hotspot VM, right?
Yes.
Okay. So you mentioned...
No, I'm representing Graal in terms of the Polyglot. Right.
In a way, I'm representing hotspot with Zulu.
Exactly. So hotspot is kind of fair between Azul and
So how important is Polyglot?
I think that's a good controversial.
So which one of us should start? So I think, in a way, Thomas presented the vision for the JVM being a host to other languages, which I think is a cool vision. And actually, I saw your talk today with a really cool demonstration of showing JavaScript, Java, and R code running in one process calling each other. So that's really cool. And I'm not that familiar with the R part of it and how that will go, but I do actually have a strong opinion about the other side for Polyglot. I think that while it's possible to run other languages on the JVM other than the ones that were designed for it like Java, like Scala, like Clojure, like Groovy, sort of. Hosting the other languages is an interesting academic exercise, but it doesn't seem to be very successful in practice. So the other languages have their runtimes. And unless you beat the runtime, like actually have a reason for people to run there other than they also want to use Java in that language and want to be Polyglot, I think it's very hard to take over the runtime from another language. So in my opinion, the focus for the JVM is JVM and JVM-based languages. We're hosting languages that already have another runtime and trying to move them over. It is somewhat of a losing proposition because we carry so much weight. I don't have a high hope of getting Go to run on Java even if it can, or JavaScript. Or Ruby is probably the closest to being successful. Even there, JRuby is a very small portion of what runs Ruby in the world. So that's my opinion, that it's kind of the Polyglot stuff or other runtimes. In a way, I think you'll probably chime in with, and you'll do those too.
I was just going to say, we chased the universal bytecode for years. J9's heritage actually comes out of Smalltalk VMs. Our first version of Java actually was Smalltalk. We just translated the bytecodes into Smalltalk. I don't think we ever shipped that, but it was our first version. And the story is great, but you just don't get the performance you want. You don't get what you need out of the platform, which is why we went the Eclipse OMR route, which is, let's take the core components of the runtime, the pieces that are shareable, and go meet the language communities where they are, most of which are writing C and C++ code to make their runtime. So let's meet them there. Let's provide high performance, battle tested, production ready garbage collectors and JITs, and work with them to integrate them into their languages to pick them up in their communities and increase their performance, and make it so that you can use the same tools across all these runtimes. That's unless you actually have to run Java code in both things, you want to do the JRuby thing and dig into the Java libraries. It's really at an operations level that you care about having common tools across all these runtimes.
Well, I mean, if product teams say it's not possible, it's for research teams validation that they try the right thing. In terms of performance, actually, I mean, we put more like our research project started like 6-7 years ago with this type of vision, and after this 6 years of research, we actually think that we have achieved the right type of performance. And for JavaScript, for example, we are outperforming V8 on benchmarks, on the Octane benchmarks that they have written themselves. So we are outperforming the best JavaScript competition on the JVM. I think that, I mean, our framework takes a very different approach. It's not about like defining a common bytecode, but it's doing this more sophisticated way of specifying the semantics to the VM in terms of interpreters. So this is the main innovation that I think over other approaches to try to fit everything into one bytecode. As for the motivation on why we would want to do that, why would you want to run Node.js on the JVM, right? It's actually surprising. A lot of partners that we've spoken to are very interested in that. And the reason for that is that they have a very big investment in Java source code. That is their business logic. And then they have new teams coming on, and they want to create like a little web service in Node.js. And then you don't want to throw away all your Java investments. And it actually can make this combination of Node.js and Java can make a lot of sense, because you have statically typed Java for defining the long-running business processes, business data types. And then you have for fast prototyping the Node.js front end. So that's why we think that this type of approach has a future and has potential people interested. And I definitely think that we can beat, in terms of performance, V8. In terms of Ruby, we are beating JRuby with 5x. 5x higher performance compared to JRuby. And this is like, for R it's actually similar, but that's because those languages haven't received so much attention compared to JavaScript. For us, really, JavaScript is one thing that validates the performance of our approach.
I'd say, part of it, I actually don't dispute the performance argument at all. I think you're right, and I think that Truffle is a really cool way of presenting the Polyglot solution. I just think that it's hard to get people to adopt it no matter what you do down that path, because they already have the runtime. It's similar to Microsoft trying to get people to move Java to .NET, because that platform could do Java. Other than some lawsuits that had an issue in the past, but it's the momentum, and from experience, it's hard enough for people to move Java from one JVM to another. Moving JavaScript from whatever they're running on to something else requires a strong reason, and that strong reason is not just performance being better now. It needs to be being convinced that that is the future, that everybody's going there. And creating that everybody's going there is about a lot more than being able to run it. And that's where I think the real challenge for Polyglot JVMs are.
Yeah, absolutely agree that performance is not the reason why we go there. It's because companies, in particular big companies that we are working with, have very diverse teams. And the development and choice of technology actually is more and more developer driven. So you acquire a new team, and that team has JavaScript running, right? And you want that team to work with the other team, and that has Java running, right? I think that's the biggest motivator.
I think the answer to that would be microservices.
I was just going to say the same thing. You know, nobody's disputing that the world is going polyglot. That you are seeing people show up and say, "Oh man, I have this this Node.js service I didn't know about, and it's critical in my infrastructure." And the answer is yes, you probably do. You're probably going to find out you have more and more of these things running, and you need to find ways to communicate between your Java backend and your Node frontend or whatever else you may be running.
Yeah, that's very painful, right? If I have a direct access to the Java data structures as opposed to defining a microservice API that is serializing, deserializing, right? I mean, I think we have a real value proposition here that goes against the microservice trend, but I think the microservice trend is coming from the fact that these polyglot options don't exist.
On the last statement, that assumes that the other languages like C++ and Node.js have a way to call Java data structures, no?
Yes, and they can call it, they can access it, they can...
And that exists now?
Yes, in the Growl project it exists, yes.
Well, it's really cool, but you should call to them is there. Let me correct it, does it exist now? Can you run it in production now? Absolutely not. Okay. So we're talking about futures.
So you can download it from the Oracle Technology Network on an early access license. If you're an Oracle customer, or then we will give you some special help with dealing with it, and we will get to production soon enough. He's always teasing me here.
Yeah, it was a tease intentionally.
What was it? Did you mention the
There's a
dates?
difference between the future things that people are working on that are really cool, and then we should all talk about the future things that are really cool. And what can you do right now? If you need to deploy something next week, what can you use? And I think that, as I said, you can access it. It's sort of early access mode. You can experiment with it. You can play with it. But you guys haven't released it in a way that you intend for people to put their production mission critical things on yet. It is coming soon.
It is coming soon, and I cannot talk about it. That's why he's teasing me.
Well, one benefit that I saw with the Polyglot, I mean, so you mentioned R, and normally we're not talking about R, but now with machine learning, and R becomes so popular with data analytics and data scientists, it seems like you can significantly speed up R and machine learning applications that are written in that language.
Yes, for R we can achieve high speedups because R at the moment is only interpreted, and a lot of R programmers are rewriting the code to C, C++ because R is so slow. And with our system, this is no longer necessary.
Yeah, quick question. How do you compare, contrast the I forget the code name, but Growl versus Swig JNI mechanisms that already exist to have to talk between Java and C++ and back?
So JNI is a huge performance overhead, and it's always a core boundary. So in our system, you can, from your JavaScript, for example, call a C function, and it will be compiled into one method.
There is work going on in OpenJDK to address some of the FFI related problems. Take a look at Project Panama for a better way to access native data structures, for a better way to deal with, call it, native libraries.
But I'll put in a Growl advocate hat for a second. The thing that Growl and Truffle are able to do that none of the other things are able to do across that boundary is actually optimize across it. So they can take it in inline and optimize across that correctly if I'm wrong. And that takes a step beyond any kind of removal of overhead. It actually allows optimizations and effective inlining to happen across the line, which is
yeah. And the other thing it allows is to have a safe execution mode where that C code is bounce checked and memory sandboxed.
So I'm a little confused. So a common thing, especially in the New York area, is calling C++ code from Java. So is Project Panama addressing that, or is the truffle aspect of Growl interesting.
At this stage, for this type of conversion between Java to LLVM, to Java to native, it's Project Panama still. But our next generation research project is bringing Java to the truffle level. So we are executing Java on top of truffle. So we are integrating Java with an interpreter written in Java on top of the JVM, and that will then allow this type of transitions. But that is not coming this year, this is coming...
A thing we are working on, a similar kind of, I said this isn't shipping product, it's stuff we're working on, is using the LLVM framework for similar benefit. So taking, when you have either source code for C, C++, or you have, or it was compiled to LLVM bit code rather than all the way down to object code, then we could do some really cool things with it from Java to that because of our LLVM backend for Java. And it's a similar thing, once you bring it into the form where the optimizers are seeing it together, you could get some really cool stuff going. I find the practical challenge there, and I think it'll hit all of us, is that the code we're running is not C source code, and it's not LLVM compiled bit code that we can consume. That would be really great. The code we're running is 15-year-old 32-bit C code in object form as it is, or 64-bit if we're lucky. So it's very common that the GIN I call, we don't get to manipulate those bits. They're x86 instructions, and the terrible thing about that is we have to assume the ordering is strong, we can't reorder things. It's all kinds of optimizations get lost unless we can recompile the source in some way, reconstruct the more abstracted form of C or that. In places where people care about the performance of that and they own both sides, if they recompile the C or C++, we could do some really great things in the future. I think that if they don't, it's very challenging because we're stuck with inherently low abstraction code that is very hard to optimize across the line. We can remove the call overhead, but not much more. I don't know if you have some views that could be on.
No, I absolutely agree with that.
So who's actually working on sort of getting regular Java bytecode shapes getting optimized? I know you guys are talking about, Growl being able to, and Truffle being able to optimize through that, but and I know that Oracle's working on Valhalla, right, and specialization and reify generics and whatnot, but is there any thought in terms of actually enhancing bytecode further? Because it seems like right now when you compile down, a lot of stuff gets erased, and the JVM ends up having to relearn and refigure out the types that are otherwise loop dynamic to it. And a lot of time in source, you actually know a lot more information. And so what are your thoughts about enhancing the bytecode and so having the front end being able to generate information that's more targeted rather than having JVM be a magical box that has to rederive the intentions that the programmer already knew? If that makes sense.
If the question is for Java or for Java-based languages or JVM-focused languages like Scala or Clojure, I think we actually don't lose that much information in bytecode. The JavaSIG compiler doesn't erase much from the point of view of the semantics. So we're talking strongly typed, not dynamically typed, right? So,
no, but I mean, I'm just talking about generics, right? They're erased the object, right? So then you gotta have PGO, and then you gotta profile the receivers and all that stuff, right?
Non-reified generics are an interesting separate subject for Java, the language, and then JVM under it.
Yeah,
but you first need to start with the language.
In my view,
I was going to say, we've been involved in the Project Valhalla work for quite a while now. We had started actually looking at something we called packed objects a number of years ago, which was taking that idea of how do you take your objects and get better locality out of them, remove the object headers, remove the dereferences from them, and all the pointer chasing. And out of that grew Project Valhalla in Panama. But the generic specialization work just introduces new problems. It's a great thing for some areas, but it gives you a problem of exploding templates. The straightforward implementation of that is to generate a new class for every instantiation of your or a generic, and that's just going to bloat your JVM.
Well, that's not really true though, right? Because you have profile information, so you don't necessarily have to do it like that.
Yeah, but that's why you could, I mean, you don't need to do this specialization at the bytecode level, because the runtime could actually be clever enough to figure out that a hash map of with an integer key is used often.
Yeah, I think that the adding primitives to collections, which I'm looking forward to seeing because I think it'll be really useful, is very different than just getting rid of the verification that's there. That's a different thing. And then I think you could say that variations have been explored. C++ has done the template thing forever. C# has good experience with non-verified generics. So it's certainly possible that it should work. And I personally wish that Java took that route when it went that way in Java 5. But I also think it's hard enough to re-steer Java away from it that I wouldn't hold my breath, is the way I put it. And without steering the Java, the language part, what we do underneath, it doesn't, changing that, going around and saying, we're going to have some Java 12 that has a new way to do generics. Somebody will have to take that on, and it's a big project. And right now, I don't see any actual activity on this. I don't think anybody's doing a non-verified generic action. The focus that you described is purely on allowing primitives within generics, but not full capture of types.
I think it's not about defining new bytecodes or anything like that. There's really only two things you need to change in the Java specification, or that are mistakes in the Java specification that make all of this so hard. Is the first one is guaranteeing object identity. I think we should not guarantee object identity for all types. And the second thing is allowing locking on all types. If you remove those two constraints from the specification, then a clever runtime can do very interesting things.
Yeah, so but that's I guess value types, right? I mean, a lot of
I think
yeah,
we're talking about different things. So that's, if you want better layout, packed objects, or you can look at the object layout project that I have on GitHub or other specifications. Those are all about how to lay objects out better, but none of them address the issue of generics being verified.
I'll give you another
needing a
example.
checklist and result.
Slightly monopolizing. I'll give you another example though, right? So lambdas, right? So right now the way they are actually modeled is through invoke dynamic, and it basically links at runtime, right? And it makes sense. It ends up being a virtual call that could be devirtualized usually, right? But a lot of times the lambda could be cracked, right? The code is right there. Yet the JVM, or not the JVM, I guess. In this case, it's JavaSIG, right? But it's translating it to effectively something that's more abstract than is there.
But the JVM will optimize it back down.
Absolutely.
But not always, right? It requires some of the receivers you see.
So the cases that really matter are where you're passing different Lambda instructions into the same common method.
Right.
And solving that problem is still an act of research.
Right, that's the inlining problem.
Yes.
Yeah, but I mean, you should actually, for this type of code, you should definitely try Growl, because we have invested a lot of effort into solving exactly that problem. And this is why for stream API expressions, we can show speedups of 5x, 10x over other, over stock hotspot, because of better heuristics. I think this is really something that should be done by the JIT compiler in clever ways, and not be too much specified in advance, because of the problems with explosion of the state, with explosion of the types. And the JIT compiler can decide to do this type of explosion selectively on the hot parts of the application.
I can agree. I think that it is the job of the JIT compiler, and much like Java, virtual methods by default are not a bad idea, but because the JIT compiler will do all the monomorphic optimizations, the same applies here. When you write the lambdas without that multiple implementation stuff, the JVM will see right through it. When it gets more complicated, that's where the JIT compilers can start doing clever things with inlining, creating specialized code paths that have unique or monomorphic stuff, and then you could start doing the bimorphic, trimorphic little things as well to get aggressive. I think that this is an area that will evolve in JIT optimization as the code we optimize evolves, because fundamentally JITs optimize the idiomatic code, and the idioms for lambdas are still evolving. So as people start making more, I'm going to borrow the term megamorphic for this, but megamorphic lambda site implementations, it presents the JITs with a challenge, but not a challenge they haven't seen before. And it might take us all a year or two to react to new coding patterns. But I think it is the right place to solve it. I'm not restricting the language for doing it.
Thank you.
I am really excited about OpenJ9 because I am imagining scenarios to use that. For example, using AWS Lambda or something like that, those kind of platforms that are charging you money for the memory that you are really consuming. But I don't know if you are currently using in production with some of your clients, IBM, tons of clients. I don't know if you have a real experience with this kind of platform in production.
So IBM actually has its own serverless platform.
Can you repeat the question?
Sorry, so the question was, does IBM have experience with serverless environments? Is that a...
No, with OpenJ9 in production environments.
Running OpenJ9 in production environments? Yeah, so OpenJ9 is our J9 VM. It's the product we've been putting out for, I'm going to blank on how long. It's been longer than I've been with the company, probably 20 years. And IBM runs thousands of products on top of this. So, we run our products, our customers run their products. It's a stable battle tested. It's ready for anything to throw at it.
But are you using right now OpenJ9 or are you using the JDK, the standard JDK?
We use OpenJ9. It's any code that goes into the Eclipse OMR project ends up in our J9 VM. We refactored it out as we've been delivering our product all the time.
Question?
Yeah, I have a question for Thomas. So how do you manage different versions when you talk about Polyglot? How do you manage different versions? Let's say I upgraded my code, let's say R version 10, let's say. How do you manage that? What do I need to worry about?
Okay, so the question is, how do we manage different versions?
Yeah.
That's a very good question. This is definitely a challenge. So, for some of different versions, we actually can. Let's say you want to run ECMAScript 5 code and ECMAScript 6 code. This is something we can support without problems because those is only on the language level. And there, what we can offer to you, for example, is to do language interoperability between ECMAScript 5 VM and an ECMAScript 6 VM, right? And in this way, you can run them isolated in the runtime system and still have like interoperability, zero-overhead interoperability between them. The type of versioning that's harder for us is when you say, I want to run a Node.js app with version 6 of Node.js and a Node.js app with version 8 of Node.js at the same time.
Python 2 versus 3.
Yeah, Python 2 versus 3 might be possible, but yeah, it's a similar problem. Yeah. So in this case, you would have to, like for Node.js in particular, at this stage you need to select a version. Because we are running at this stage the Node.js code unmodified and not on top of our LLVM Bitcoin interpreter. For Ruby, we can support multiple versions at the same time. But as for Node.js, for example, we are fully compatible with V8. So for us, upgrading to a certain version of Node.js is almost no work. So the most likely scenario is that we will be able to offer, like, you basically, when you create a GraalVM or when you create a GraalVM distribution, you will be able to select a Node.js version, a Ruby version, a Java version, and this will be your polyglot environment, but you can select from multiple of these versions.
The other question I have is, suppose you are running a C code which is a malloc, so how does it translate to your heap?
Yes, so there's two choices for running the C code, the LLVM bit code. One is unsafe. There we just directly call malloc, and it's fully compatible with you would usually run the C code. In the safe version, we also can run the C code in the safe version. There everything is sandboxed, and there malloc essentially allocates a Java binary. The safe version is a little slower than the unsafe version. The unsafe version is about 10% slower than as if you would compile it with LLVM at this stage. But the unsafe version is a little bit slower. but it provides you with the safety guarantees. And there, the unsafe version can interact with system calls without problems. The safe version has to be kind of sandboxed and cannot call out to the system. The application scenario of the safe version is in particular for example, C extensions in Ruby or R modules that contain native code, and you want to execute them sandboxed in your environment. So there's really these two distinct versions.
So, speaking of like the Jigsaw changes for JDK 9, what kind of impact will that have on cross, more like backend tools? For example, like the Java agent specific stuff that kind of potentially can break things with Java or with the Jigsaw.
Sure. So Jigsaw enforces a lot of stronger security rules. And I believe the default has been to change agents to limit some of their abilities, though there are still APIs that will allow you to inject. Hesitating in how I'm saying this because I haven't played with this particular area in a lot of detail. I believe you can still work around all the limitations if you have an agent. It just takes a little more work to do.
Oh, if you turn the right flags on.
If you turn the right flags on, if you inject, you can use your agent to load extra classes into the module and change the modules to export more.
I think if you look at it from a panel perspective, we're probably all going to say, well, I mean, whatever Jigsaw is, we'll support it. It's not really interesting from a deathmatch point of view. We're all going to do it. We're all going to do it right. You know, it's sort of a cool but boring subject. I'd like to talk about what we can actually do today. Let's get some, you know, anybody want to talk about garbage collection?
So there's certainly a lot of new functionality added to the JVM, new performance, lower garbage collection. So how does that affect the footprint if I'm doing like IoT applications in a reduced environments? I mean, can I still use these same JVMs in those environments also?
You want to start?
Sure. So for IoT, it really depends on what kind of device you're targeting. If you're targeting the sensors at the edge of your network, Java might not be the right choice. If you're targeting something that has a little bit more memory and a little bit more processing power, then a stripped down JVM probably is a viable target. And the limit of what kind of processing power and what kind of memory you get on these devices, most devices come with more and more memory, more and more processing today, so Java becomes a better and better target, especially if you are able to subset the platform or shrink the platform. For your question about Java 9, JLink is a new tool that's coming there that will help make smaller runtimes and smaller platforms.
So I think we actually have a lot of experience with that side of it because one of our major commercial sides of Zulu is Zulu Embedded, which goes into millions of routers and printers and soon car infotainment systems, exactly the levels that they're in. And I think we've been starting with what the edge of a practical Java SE and embedded is. I would place that edge today at somewhere around 11 to 20 megabytes of storage to hold the bits needed for the JRE. And from a footprint perspective, in the mid to high tens of megabytes practically. That's true for basically a stripped down, optimized 32-bit JVM for an ARM32, for example, or PowerPC 32. And we do millions of devices running that exact thing today. As I said, putting it in your light bulbs, especially, probably not. And I'm kind of happy it's not given the recent hack on light bulbs. It's not Java's problem this time. But once you go to the embedded stuff, once it's able to run the numbers I said, I think that footprint is there in Java 8 already in the most compact profile. I'm actually, I have a little bit of cold water to throw on people that hope that JLink are going to reduce the footprint. The practical, smallest compact footprint of Java 8 and Java 9 are not going to be very different. Because the base profile for Java 9 includes roughly the same base profile for the smallest Java 8. So you're not going to see a significantly smaller disk footprint for what you have. You're not going to see a very different memory footprint, because fundamentally the memory footprint is the code you actually run, and that isn't changing. So we're going to see similar in Java 9 and Java 8 in practical experience, I think, unless somebody goes and builds a tiny JVM, like a Java ME style JVM, but I don't see anybody doing that. We're not.
Well, I think, yeah. So our answer to the embedded space is to do a complete AOT compilation, and an AOT compilation that includes a closed world analysis. So we are taking your Java application, we are looking what parts of the GRE it is actually using, and then completely turning that into machine code. And that machine code contains a garbage collection system, but it does not contain any JIT compilation system, no class loading system or anything similar, which makes that type of native binary pretty competitive with, let's say, Go or Go binaries or C++ binaries. Yeah, it is a certain type of space that we address there, because our limitations are that we do not support dynamic class loading, and we do not support all sorts of reflection. But if you're interested in like super ultra low footprint and startup here, we can give you that with those restrictions. And you can still use Java as a language and be competitive in terms of hello world with C programming. Because we think Java has the better tools to program, and it has the automatic memory management features. So we actually would like Java to be even used in contexts where at the moment people are going to C because of the footprint reasons.
So when running, so it's pretty common to run Java inside of a Docker container, for example. But one of the problems with that is having like an absolute memory limit, where if you hit that, you get out of memory kill, kind of a thing. So it'd be really nice to be able to set like an absolute limit that your JVM will not ever exceed. Do any of your platforms really enable that?
So I'd say we did two sides of that today, Wesley, and that's today shipping product production worthy thing. I want to highlight today. So one is you can absolutely limit the memory footprint, and in fact in Zig we take memory management seriously. We'll go grab the physical memory that guarantees that it exists, refuse to launch a JVM unless it knows that it will not run out of that memory, and then keep it within the lines if that's what you want. But the other cool side of what we have is a cool side effect of our garbage collector is that it's a fully elastic garbage collector. And what I mean by fully elastic is every time we allocate more Java, every time we allocate a TLAB for Java, which is 2 megabyte chunk for more objects, we go and get that from the kernel. We don't keep it around. And every time we garbage collect, we free everything free back to the kernel. So the garbage collector is absolutely elastic, like normal processes are, rather than go sit in the memory. And within that, it could live within what we call a reservation, an actual guarantee of how much memory you will have, and then an elastic headroom. An elastic headroom could be shared across containers in a common host. So if you look at, when you run just one JVM, 2 JVMs, it's not that big a deal. If you're running 20 of them together or 50 of them together in a host, and hosts today are, half a terabyte in size, so that's not a big thing. Then being able to elastically share headroom memory that is 10 times the size of your normal JVM, because it's there, and it's not 10 times the sum of the JVMs, it's just peak capabilities, insurance against memory leaks, pauses, other things, is very powerful. This is DNA we had from the day when we used to build monster multi-tenant machines for Java. Our Vega hardware in the previous decade would host 100 JVMs in one and had strong multi-tenant capability. The DNA for that came from there. We haven't been able to use it much until containers came around. But with containers, we have an absolutely dynamic in elastic JVM, it doesn't hold onto memory, so the empty memory is available to all to share.
We have some similar technology with respect to the garbage collector heap. We call it our softMX. You can set a maximum heap size, but you can also set a softMX, and then which is the maximum that your JVM is allowed to use. And then using things like JMX beans, you can come in and dynamically change that softMX and have your JVM release the memory back to shrink its heap down to that particular size.
So is that the overall process memory usage, or just the heap?
Just the heap.
Okay.
So we support the process limit for our embedded version because there is no JIT compilation or other artifacts that need allocation. And we actually would say if you're really severely memory restricted and you can live with the limitations of not having the dynamic class loading, then this is probably your best choice because you are not wasting any space for metadata or any space for other GM-related data structures.
So if you look at it from a actual production experience, the thing that tends to hold you back from shrinking JVMs is not what footprint can you live in, but the owner of that JVM will only live with so much, and that so much is however much they think they need times 3, or some other number. They will want headroom because they don't know what's going on, they don't know what peak goes on, they don't know that they're not going to get a 300 megabyte document to process. So they pad, and they pad with dedicated memory per instance, which turns into dedicated memory per container, which then turns into how much Intel Kerberos you need. The only way to get to people to give up that dedicated padding is to give them other padding. Not to, like, if you can shrink it, it's absolutely known, it's deterministic, you've tested it to the worst case, then you know what you need. How many people do you know that actually feel that about their production application? So in practice, the padding has to exist, and shared padding is dramatically more effective than dedicated padding from a memory utilization point of view. And that's where being able to dynamically extend and shrink is there. We describe our headroom as insurance memory to people. If you end up using it, depending on the mode, you could do best effort, but if you end up using it, you get warnings. You're above your configured limits. You shouldn't have been there, but boy, are you thankful you didn't have an out-of-memory crash, right? It's still running. The headroom's there, plenty of headroom for everyone. If everybody used it at the same time, we would have a problem, just like any insurance company would. But if you're actually playing insurance, then it's a very effective way to do it. And what happens is people will give up their private local thing, not completely, they're still pad by 1.5x instead of 3x, and then use the insurance for the rest. But that's how we see the actual production multi-tenant environment evolve to because of people needs, right? Not the rest.
Everybody remember my safe harbor slide? Good. We've also, taken a look at similar things where I believe the stat is that 30% of all servers are sitting idle, and so we've been working on our VM to make sure it detects when things are idle and is able to give back memory it's not using, so that becomes headroom for everybody else.
Okay, so in the world of microservices and now especially serverless, where a method has to be created on the fly and then it's gone, is Java the right language to create these things that appear and then go away? I mean, of course, there's the warm-up period, right? That what they worry about. So is Java the right environment for serverless?
I think it should be, and we're working on exactly that problem. But I think that the fair thing to say right now is that there are, certainly on the warm-up side, there are issues. So I showed some of the warm-up things that we do, just bring the speed up to the front. But in our current shipping product, that still means that a lot of JIT optimization effort will be happening really quickly, but it's still CPU spent on startup. Our goal is to get to as close to instant start of a JVM as we can with fully optimized, effectively JITted code with high speculative optimizations in it. But that's futures.
similar to Ready Now, we do a lot of saving of AOT code, a lot of saving of profile data to make sure that you get back into peak performance quickly. This is all done through our shared classes cache. And so we've seen when experimenting with serverless platforms that you can get up and running very quickly. What serverless platforms do to take away some of the cost of those cold starts, though, is they keep your JVM around for some length of time. And so that cold start problem is only partially going to be addressed by the VM. Part of it's going to be addressed by other factors. Just to continue on that vein a little bit further, about 3 years ago we did a multi-tenancy prototype. We released early access builds. I'm sure you can probably still find them online, where you could run multiple applications completely isolated inside a single JVM. You could set file resource limits, you could set all kinds of CPU limits for them. And I think we're going to end up finding that the world is going to move back in that direction again. Some things want a pure VM, some things want a Docker container, some things you want to just run multiple copies of them inside one VM.
I think operationally what you said is very right. The cloud providers, the various cloud providers of serverless are compensating for these by just keeping them around long enough and figuring out the math of how long is worth it. And that's what they're going to have to do until it gets better. But it's hard to argue that Java is not a lot more costly to get off the ground and starts off much slower than something like Python.
Yeah, that's why we think we need the full IoT solution for Java, where Java is competitive with C and Go in terms of startup. It's actually addressing in particular people who would think about moving to Go because of the startup or footprint issues. We can provide the same thing for Java as long as you restrict your Java to need no dynamic class loading. The other point regarding the serverless environment that I would like to make is that I think one very important point in the serverless environment, or one macro trend nowadays, is that moving around the data is kind of expensive, but moving around the programs actually becomes less expensive over time compared to the data. And this is why we think that embedding a language execution environment in a data processing environment, like a database, is becoming more and more attractive. And that's why one focus area where we are going is to say, well, you can run either on hotspot as your server middleware, you can run standalone IoT compiled somewhere, or you can also run the same code inside your Oracle database, inside your MySQL database, or similar. And I think that's a very important feature that makes us ready for this serverless computing architecture.
I'd say if you look forward, we actually look sort of beyond AOT. AOT is a trade-off that we don't want to take. We don't want to limit dynamic loading. We don't want to limit features. We don't want to only work if you didn't use them, because it's actually really hard to stay away from using method handlers, for example. The approach we have going...
So method handlers are like not a problem, right? Because at this stage, all of the method handlers that are generated by JavaSIG can be resolved at image submission. Okay. It's like similar to this retro lambda, which is as a con.
There's the dynamic resolution of them across JDKs, but the parts we're looking at is take speculative optimization, for example. Much of the speed we get comes from that. I'm not sure how much, but if a wide guess is about 3-to-1 ratio between if you can speculate or can't speculate. And maybe we're talking about the same thing when we talk about IoT, but to me it's being able to compile things that are speculative and run them in the future, which requires more than communicating just the object code to the future. So we're looking at, think of it as achieving the full speed of what you do today in the runtime, but being able to get back to that speed in the future. And I very carefully do not call that AOT, because AOT suggests you do not recompile it later, you do not replace it on the fly, you lose some of the capabilities. So we're talking about going to full speed from the start, which is, we see as absolutely possible in what we're doing, but it's not what we're shipping today. whether it's a year or two down the road, we'll see, but we're looking towards that level of speed so that you basically hit the ground running. If you want to think about it as when the JVM wants to compile something and optimize it, chances are we, in the past at some point, very near to here, did exactly the same thing, and we already have the answer. And the answer including all the assumptions and speculations that we're doing. And once we can close that loop, we could get to a very quick start from a standstill to fully optimized code without warning.
AOT is a great band-aid to fix the startup problem. If you save away your AOT code and you save away your profile data, you still want your JIT compiler to let higher tiers and higher optimization levels kick in. And that's what the approach J9 has taken up to today.
So I read a recent paper. So we all know about increasing numbers of cores and numbers of cores is going up and up. I read a paper probably about 6 months ago where it said that we've reached the limit, the number of cores, because of the heat. And there's a term called dark silicon, where most of the cores on a chip are not engaged, they're turned off. So, you know, how is Java going to approach the future? I know I've been talking to Brian Getz, I mean, we're using more and more cores in the JVM, et cetera, et cetera. But what happens when we reach a limit? How can we get faster with the JVM and maybe a heterogeneous environment as opposed to a homogeneous environment with cores? Maybe there's FPGAs, TPUs, et cetera, et cetera. How is the JVM going to address that?
So you gotta just, you have to agree with the premise of the question, I think, and I don't. We've heard people say that Moore's law is stopping for many decades now. And I think we always find a way to push through, whether it's faster, more silicon, for one purpose or another, more cores or faster cores or new features that go faster. But if we clock speed over time, it hasn't let up. And I don't see a reason to think it's letting up. If you want reasons to believe that we're far, far away from breaking the core limits, at Azul we shipped an 864-way SMP 10 years ago. And yeah, it wasn't as fast or as hot as an x86, but that level of core parallelism is not a fundamental problem. If you look at GPUs, they go much farther than that. And I think we have still a lot of growth to see in the platforms. They're not stopping. Now, they might stop looking flat. You know, a single socket has now got more than one Luma node in it, actually. But within those shared memory infrastructure things, I think we're still going to see a lot of growth of the amount of crunching power for regular shared memory, Java or C or other applications that are not sent off to coprocessors. And we've seen steady growth, and I don't think it's stopping.
So regarding the number of cores, I think people will always want more, so the number of cores will never be enough, which means real scalability will always have to be with number of machines. And I think one of the success stories around Node.js and an area where Node.js has kind of been more focused on compared to Java is this multi-machine scalability, whereas Java has, I think, for too long put the bets on just a big application server on a big machine. And I think we should also, as a Java community, think more about the multi-machine scalability. With respect to GPUs, one of the research areas we are focusing there on is to allow the memory layout of the GPUs to be accessible from the application, so there is no coupling involved. So, because the GPUs usually take a very special type of memory layout, and what we are trying to do is to present this memory layout as it is to the running program without marshalling it and copying it around in the main memory.
For GPUs, we're also seeing the coprocessors. We're seeing the cost of using those is mostly dominated by the cost of getting the data over to the coprocessor. And so hardware vendors are looking at how do we decrease that cost, how do we make it cheaper for you to get your memory over to the coprocessor, which means you can use them in more more cases and for more data.
Since we should be arguing, let me argue. I actually think Java is currently the best language we see at using lots and lots of machines. I wouldn't give credit to JavaScript in that at all. It's just credit to an industry that's learned to scale across machines, to not put single point of failures, to not put single vertical scale needs. If you actually look across the board at projects that happen to be in whatever language and use a lot of machines successfully, let me name a few: Cassandra, Kafka, Hadoop, Solar, Elasticsearch, Flink, and we could keep going with it, Storm and all the rest, Spark, a little bit of project there. All these use massive amounts of nodes, and they're all written in Java.
Yes, I agree. I'm very happy about that, actually.
Yeah, exactly.
I just think that there's not been, like, if you think about innovations from the core Java platform for these platforms, right? I mean, there hasn't been a lot of work in the Java language or Java specifications to particularly support it.
So the one that hurts me the most is, why the hell do we still have to use a third-party library to process JSON objects?
Absolutely.
That's not a JVM problem, actually.
Yes.
We've got 13 options, but we don't know which one to use.
100% agree.
And that really should be a part of the JDK. But I think fundamentally...
Also, your proposal on array layouts, I think, is really great. I think the fact that we don't have this array layout in the standard, I think it's a mistake.
And we'll see once the value object stuff gets through, we'll see if we get additional things through, or packed objects. But again, I think that across machine scalability, the trend towards tens and hundreds of nodes being a scale limit, or scale behavior, is an architectural application scale. And I actually like that we are living in a world where both the microservices or isolation trends, whatever you want to do the trend du jour, and the behavior of teams and isolation of decisions within DevOps teams, for example, allows us to be truly polyglot across instances. So we have a free mixing of things built and whatever the right thing to build them are, because we try not to build one big monolith of anything. And whether that's out of Java or anything else, as long as you can isolate it behind its functionality, build it in whatever you like to build it now, and replace it tomorrow in whatever else you'd like to build that. The evolution of one to another is a good thing. Twitter is probably a classic example of taking an entire company infrastructure from Ruby to a Java-based, to a JVM-based implementation, not by trying to run Ruby on JRuby, but by actually saying, let's just rewrite all the functionality piece by piece until we're done. And the ability to do that is there because the design at the infrastructure and application level did not assume a specific language. So for example, RMI would probably be a bad idea for how you communicate between processes, because it'll tie you into Java and a version of it in that, right? A version of the RMI that you're using. It's, as much as we live in the JVM world and we want that to be the big one and succeed, I think that true interoperability is more important than anything else, and that's done at the process or container or VM level, where the other side could be whatever it wants. Hopefully that other side wants to be Java.
Yeah, but I think you want both, right? You want some architecture where some components are loosely coupled, but I think if there would have been a high performance, first of all, if there would have been a high performance Ruby implementation like ours back then, Twitter wouldn't have had to write everything in Scala, they would still run on Ruby. 100% convinced of that. And the second thing is, even if you have this like separation, you might still want to have like do the rewrite like partially and say like, well, in this microservice I'm using Ruby and Scala, and this one is now only Scala. But we get in particular is like also as Oracle, like we often acquire some company. And every company has their own technology, and you need to, as quickly as possible, integrate it into your software stack. So in general, I agree. There's some benefits to do the loose coupling, but you should do the loose coupling because of your architecture. In this case, requires you to do, and not because of a technical limitation.
So I know this is Gil's favorite topic, but what are the other two companies thinking in terms of handling sort of half a terabyte, terabyte heaps, right? So memory management, obviously, you know, Oracle's got G1, and then Red Hat's working on Shenandoah. I don't know much about the IBM's GC options, but is Oracle Labs, for example, doing any sort of research into, you know, GCs that handle heaps that size? Also, you know, we were talking earlier about larger core counts. I think right now there are some things that would just, like if you had an 800 plus core hotspot, it just wouldn't scale because, you know, for example, save points are global, right? So you can't start bringing 800 threads to a stop. And I think there's some issues also with GCs in terms of like how they share work, you know, more architectural designs. So I'm just curious what, you know, IBM and, I mean, Gil, you know, feel free to obviously, but you know, what IBM and Oracle are researching or thinking about in that space.
So we've done a lot of work to make sure our GC scales across hundreds of threads. We've seen power boxes that have hundreds of threads and made sure that we're able to run and scale well across them, 500 plus gig heaps. So we've done a lot of work in those areas already. You can pick up J9 today and run it in those kinds of environments. And you should be having no issues there. You mentioned G1. IBM's equivalent of that is the Balance GC. It's another region-based garbage collector. Aims to keep pause times consistent and small.
So regarding garbage collection, we welcome Shenandoah as a very interesting choice for OpenJDK, and we are happy that Red Hat is contributing that. We are expecting them to contribute the GRAL barriers soon. In the GC area, one of the things we try to do is to kind of avoid GC completely, but we are focused there not so much on the terabyte heaps, but on request-based processing. So this has to do with our database integration, where we expect triggers to run and basically be able to discard all of the garbage that trigger is creating or that user-defined function is creating for a certain row. In our closed load analysis, we also do some static analysis that is then verifying this type of zone allocation. And then, so we're kind of more in the area of avoiding GC at all, if possible.
So that's pretty interesting. So is that like a region memory management manual, or is that more like escape analysis that GRAL does?
No, that is a region memory management.
And this would be something that would be
visible
through Java.
This is only available in GRAL's embedded version, like when you create this embedded, because we use it for our load balance embedding, for our database embedding. This is not something that would be available on Hotspot. On Hotspot, we go with the default options, G1, and Shenandoah as another interesting choice.
So I'd say, to begin with, Java is a garbage collected language. If you want to avoid garbage collection in Java, good luck. Or there's some people here in the room that probably have built a zero GC framework. Anybody want to raise their hand? There you go. Now, have you been able to use any third-party code in that?
No, not in fast.
When you use third-party code with your beautiful zero GC framework, what happens? It allocates stuff in GCs, and your beautiful GC framework now pauses. To us, and yeah, this is my favorite thing, we believe garbage collection is easy and shouldn't pause. Or shouldn't pause more than the OS does already. And we've brought it to that level, not for 500 gigabytes, but for 1 gigabyte, and 2, and 5, and 10, and 20, and 2 terabytes. It behaves the same across that, the way it should have been from the start, in our opinion. The notion that it's okay for a computer to take a vacation while it's running your code is a wrong design notion, and it's not Java's fault. There's nothing inherent to Java that says we need to do that. We're the proof of that. So instead of limiting the use of memory, we encourage using more memory. Instead of reducing allocation, we think allocation is a great thing. And if you want to run fast and you're allocating for no reason, go ahead and optimize. If you want zero GC, that works fine too. But generally, we see the various band-aids around as duct tape put on a solution because the underlying platform just doesn't do its job right. And once you get the underlying platform to do the job right, we're done. Now, the G1 and balance collectors are sort of the state of the art in other JVMs. And they are very good. We're about 500 times better. And that's not an exaggeration, that's a comparison of pause length. So, you know, we can keep putting the band-aids on and we can keep looking for ways to reduce the stress on this thing and try not to hurt its feelings too much by allocating objects. Or we can just make it work, and we think that making it work is the answer. To chime in on the Shenandoah thing, the credit I'd like to give Shenandoah is this is the first team that is working on the right problem other than us. Addressing the problem starts with admitting the problem exists. And when you admit that the problem is, you need to be able to compact memory without pausing, not with really short incremental pauses. Then you can go solve it, and Shenandoah will attempt to solve it. I think that their approaches are interesting. When it's actually running in full production mode, we'll be able to just compare and we'll have a true competitor at that time. Until then, remember the here and now, we've got one. It's shipping, people are using it. It works for mission critical better business applications already.
Okay, so I think we have to wrap it up. So I wanted to thank these gentlemen. I want to thank Thomas from Oracle, Gil from Azul, and Dan from IBM. So thank you very much, gentlemen. We have about like 5-7 minutes. If you want to come up and ask these gentlemen some questions, feel free. So from the JavaSIG, we'll see you next month.